Hello everyone, welcome to lecture series on power system protection. Myself Rajeshwari Ananavar, working as assistant professor in the Department of Electrical and Electronics Engineering, KLS VDIT Halyal. Today we are dealing with 5th module, lecture number 39. In previous lecture, we discussed protection of a transmission line against direct lightning strokes. In that, in order to protect the transmission line against the direct lightning stroke, we do run a ground wires parallel to the live transmission lines. So these ground wires will be made of a ACSR material which is going to have a better insulation compared to the transmission line. So these ground wires will try to attract these lightning strokes themselves rather than passing them to the transmission lines. So these will be connected in such a fashion, so they will run parallel to the transmission line, and their care should be taken that these ground wires should not be kept exactly at a exactly above this transmission line. So because there may be a chances of a what we can say, the sagging problem because of the ice loading, so there may be a short circuit between the two ground wire as well as the transmission line. So in order to avoid all these conditions, there should be a adequate clearance between the ground wire as well as the transmission lines. And also we discussed the protection of the station and substations from the direct strokes. In order to provide the protection not only for the transmission line, for station as well as the substations, we do have a different protective devices. With the help of a ground wires also we can provide, so where the entire ground wires will be covering the station as well as the equipments below and above the stations. So all will be comes under the zones of protections of the ground wire. If ground wire feasibility is not ground wire connections is not feasible, then we may go for the vertical structures known as a mast. So with the help of these vertical masts also, the protection for the station as well as substations were provided. So these 2 points were discussed in the previous class. Moving on to the today's lecture, today we are going to discuss the continuation of the previous class, that is a protection against traveling waves, insulation coordination, basic impulse insulation level. So the 3 concepts we are going to learn today, and after this lecture the students will have a better understanding of protection against traveling waves, concept of insulation coordination as well as the basic impulse insulation level. As per the Bloom's taxonomy, the today's concept comes under the second level understanding, so L2. So we'll begin with the protection against a traveling wave. So first we need to understand what is the meaning of a traveling wave. So this traveling wave is nothing but it is a temporary wave that creates a disturbance in the system and moves along the transmission line at a constant speed. Okay, so it is because of the lightning phenomena. It is a temporary wave which is present in the transmission line. Okay, so such type of a wave occurs for a short duration, that is with respect to the microseconds, but causes a much disturbance in the line. So the transient wave is set up in the transmission line mainly due to the switching actions, faults or the lightning phenomena. So the because of these traveling waves, in order to avoid protection against these traveling wave, we need to have some protective devices, or we need to have some protection against these traveling waves. So shielding is a shielding the line, that is that we all what we have learnt in the previous class, that is providing the ground wires, that is also nothing but the shielding the line, and stations by overhead ground wires, masts or rods undoubtedly provides a adequate protection against a direct lightning stroke, and also reduces electrostatically or electromagnetically induced over voltages. Okay, so with the usage of these ground wires, which is nothing but the shielding the line, they are going to provide the adequate protection to the transmission line, okay, against the direct lightning stroke, as well as giving the protection to the station, substation also. Okay, but such a shielding does not provide a protection against the traveling waves which may come in over the line and reach the terminal equipment. So as I have mentioned, because of these lightning phenomena, so there are some waves will be produced. These waves will try to move through the transmission line. Okay, and for a few seconds, because though they are present only for a few seconds, but their impact is very very severe. So we need to give protection against such a traveling waves. So this shielding is not sufficient to give protection against such a traveling waves which may reach the terminal equipment. So such traveling waves can cause the following damage to the electrical equipment. Internal flashover caused by the high peak voltage of the surge may damage the insulation of the winding. Okay, it may damage the insulation of the winding. Internal flashover between interturns of the transformers may be caused by the steep fronted voltage wave. So because of that steep fronted voltage wave, the transformer may be, the interturns of the transformer may be getting affected. External flashover between the terminals of the electrical equipment caused by the high peak voltage of the surge may result in damage to the insulators. Okay, so it may damage the insulators. Resonance and a high voltages resulting from the steep fronted wave may cause an internal or external flashover of an unpredictable nature, causing building up of oscillations in the electrical equipment. So it may cause oscillations in the circuit. So with these all damages caused by the traveling waves, we need to have protections. Hence, it is absolutely necessary to provide some protective devices at the station or substations for the protection of the equipment against the traveling waves caused by lightning. So in order to protect these traveling waves, in order to protect the equipments against the effect of these traveling waves, the following equipments we are going to use: rod gap, arcing horn, lightning arrestor or the surge diverters, as well as the surge absorber. Now one by one we'll see what are these equipments and how they are going to give protection to the equipment. First we'll deal with the rod gap. A rod gap provides the simplest and cheapest protection to the line insulators, equipment insulators and bushings of the transformers. So it is basically giving a protection to the insulators of the line, equipment as well as bushings of the transformers. In case of a transformer, rod gaps, which are called as the coordinating gap, are installed to protect the apparatus. Rod gaps provide a backup protection to the bushing of the transformer in case of a primary protective devices, that is a lightning arrestor, fail. So as I have already mentioned, so these transformers will be always provided with a lightning arrestor. If these lightning arrestors fails, then automatically these rod gaps will be acting as a backup protection. So this is a arrangement of the rod gap. What we have, this is a bushing of the transformer. So here we can, so this is a bushing of the transformer. As you can see this structure, this is a bushing insulator of the transformer. Okay, a rod gap consists of two rods of approximately 1.2 centimeter diameter or square. So these two structure, what you can see over here, one at the top and one at the bottom, these two rods, okay, made up consisting of 1.2 centimeter diameter, either square or a circular fashion, which are bent at a right angles. So which are bent at a right angle as shown in the figure. One rod is connected to the line, with the other rod is connected to the ground. So this rod is connected to the line, that is a transmission line, and whereas the one more is connected to the ground connection. So whatever we are representing here, this is for the transformer bushing what we are showing. In case of a transformer, they are fixed between the bushing insulators. So these are nothing but the bushing insulators, what we can say. So between these two bushing insulators, we are fixing up these rod gaps. Whereas in general, for the general protection purpose, these first top will be connected to the line, whereas the second will be connected to the ground potential. In order to avoid cascading across an insulator surface under very steep fronted waves, the rod gap should be adjusted to break down at about 20% below the impulse flashover voltage of the insulation of the equipment to be protected. Okay, in order to avoid the what we can say the breakdown of the insulation of the equipment, so these rod gaps will be the what we can say the gap between the rod gap rods adjusted such that it should break down at about 20% below the impulse flashover. Okay, so if the flashover occurs at some voltage level, so below 20% of that flashover, so it is going to be breakdown. So this is a arrangement what we have, and this is, as we can see here, this L, the rod gap. Okay, so this is a rod gap we are going to adjust, and this L1, the distance between these two is selected such that L1 should be greater than L over 3 or L by 3. Okay, so this distance we need to mention. The distance between the gap and the insulators should be more than 1/3 of the gap length, that is L1 should be greater than L by 3 in order to prevent the arc from being blown to the insulator. The major disadvantage of a rod gap is that it does not interrupt the power frequency follow current after the surge has disappeared. This means that every operation of the rod gap creates an ULG fault which can only be cleared by the operation of the circuit breaker. Okay, so the main disadvantage of using this rod gap is it is not going to interrupt the power frequency follow current after the surge has disappeared. Even though surge voltage has been disappeared, it is not going to interrupt the normal power frequency current. So because of which it may create a LG fault also, because one end is directly connected to the ground connection, so it may create a line to ground fault. So this can be cleared with the help of operation of the circuit breaker. Thus operation of a rod gap results in a circuit outage and interruption of a power supply. The next we have is the arcing horn. The damage to the line insulator from a heavy arcs formed due to over voltages is a serious maintenance problem. Several protective devices have been developed to keep an insulator string free from arc. Arcing horn is one of such a protective device. In order to protect the insulators from a heavy arcs, so these arcing horns will be chosen. Arcing horns will be provided in the systems. Arcing horn consists of a small horns attached to the clamp of the line insulator string. So this is a insulator string what we have here. Okay, so this is a complete insulator string. Okay, above and below which we will be using the arcing horns. These are called as a arcing horns. Horns with a large spread both at the top of the insulator and at the clamp are required to be effective. This is as shown in the figure. So these should be very much effective. In case of a lightning impulse, the arc form tends to cascade the string. In order to avoid this cascading, the gap between horns should be considerably less than the length of the string. Protection of a line insulators by arcing horn thus results in a reduced flashover voltage. The protection of a line insulator by arcing horns is specially used in hilly areas. The grading ring, when used in conjunction with an arcing horn fixed at the top of the insulator string, serves the purpose of an arcing shield. In the event of an arcing forming following a flashover caused by some type of overvoltage, the arc will usually take path between the horn and shield, and insulator string will remain clear from the arc. So this is the function of the arcing horn. The next we'll move on to the lightning arresters or the surge diverters. So these lightning arresters, which are also known as the surge diverters or the surge arresters, they are connected between the line and the ground at the substation and always act in parallel with equipment to be protected. So as we have already learnt in single line diagram of the substation. So please recall the single line diagram of the substation which we learnt in the CAD class. That is the add-on course CAD class. In order to for the drawing of the single line diagram, we used to make use of these lightning arresters. Okay, so as and when the line starts, we need to provide the lightning arresters. Okay, so connected between the line and ground at the station, substation, and always act in parallel with the equipment to be protected, and performs their protective functions by providing a low impedance path for the surge currents, so that the surge arrestor protective level is less than the surge voltage withstanding capacity of the insulation of the equipment being protected. So how these are going to provide means they will be creating a low impedance path for the surge currents. Okay, so instead of the surge current flowing into the line, transmission line, so always we know the current will choose the lowest resistance path. So comparing to the transmission line, these lightning arrestor path will be having a least resistance. So through these lightning arrestor path, the surge current will flow to the ground rather than flowing into the transmission line and damaging the equipments. So like this, these surge arresters will be having a low impedance path for the surge currents. The main purpose of lightning arrestor is to divert or discharge the surge current to ground instead of passing them into the transmission line. So they will divert them. So they will what we can say divert or discharge the surges to the ground potential. The action of the surge diverter is explained with a figure 8. When the travelling wave reaches the diverter here. So this is a voltage characteristic of the surge diverter. When the travelling wave reaches the diverter, it sparks over at a certain prefixed voltage as shown by point P. So this is a point P and provides a relatively low impedance path to ground for the surge current. Okay, the current flowing to ground through the surge impedance of the line limits the amplitude of the over voltage across the line and ground, known as a residual voltage, represented by the point P. So this is a point P, to such a value which will protect the insulation of the equipment being protected. So if these surge lightning arresters or the surge diverters were not there, so that surge current may reach to a peak value, so which is represented over here. So this is a surge voltage without protective devices. Because of this, it is restricting the surge current over itself, surge voltage here itself and the point P. Okay, and the current flowing to the ground through the surge impedance of the line limits the amplitude of the over voltage across the line and ground, known as a residual voltage. So that is represented by the point Q over here. It is essential that low impedance path to ground must not exist before the over voltage appears, and it must cease to exist immediately after the voltage returns back to its normal value. So the care should be taken that under normal operating condition, so these lightning arrestor path, it should not have a low impedance path, and as and when the surge attacks, the surge voltage appears, at that moment it has to create a low impedance path, and it must cease to exist immediately after the voltage returns back to its normal value. Once the voltage reaches to its normal value, it has to cut down its action. An ideal lightning arrestor should possess the following characteristic. It should not draw any current at normal power frequency voltage. That is, during normal operating condition, it should not draw additional current. It should break down very quickly when the abnormal transient voltage above its breakdown value appears, so that low impedance path to ground can be provided. The discharge current after breakdown should not be so excessive so as to damage the surge diverter itself. Okay, so the discharge current of these lightning arrestor after the breakdown, it should not be a very high value, it should not be so excessive so that it can damage surge diverter itself. Okay, so it must be capable of interrupting the power frequency follow up current after the surge is discharged to grounds. So these are the some requirements we expect, or the performance we need to take care of about the lightning arrestors. The next we have is a surge absorber. A surge absorber is also known as a surge modifier. It is a device which absorbs the energy contained in a traveling wave and reduces the amplitude of the surge and stiffness of its wavefront. So this surge absorber is nothing but it is going to absorb the energy of these traveling waves associated with respect to the, and also reduces the amplitude of the surge, that is a voltage. Better method of reducing risk of traveling wave is to terminate the line at a distance of 0.8 to 1.5 km from the station and to connect it to a station with an underground cable. This method has the following three advantages. The cable gets shielded from all electrostatic phenomena and from accidental ground through various causes. When the traveling wave enters the cable from the overhead line, they are reduced in magnitude to about 20% of their incident value because of the ratio of natural impedance. When the traveling wave is transmitted into the cable, it's get attenuated rapidly due to the dielectric loss taking place in the cable at high frequencies. The most modern surge absorber. So this is a surge absorber that known as a ferrantic surge absorber. Okay, so it consists of an air cored inductor. This is a air cored inductor connected in series with each line. So this is a air cored conductor connected in series with each line, surrounded by a grounded metallic sheet called a dissipator. So this inductor is surrounded by a metallic sheet. This is a metallic sheet called as a dissipator. Okay, and this is a air cored inductor. The inductor is magnetically coupled but electrically isolated from the dissipator. The inductor is insulated from a dissipator by the air, hence it is known as an air cored inductor. The surge absorber acts as an air cored transformer whose primary is the inductor and dissipator is a short circuited secondary of the singleton. So this we can relate it to a air cored transformer where that inductor is acting as a primary winding and the dissipator is acting as a secondary winding of the transformer. Whenever the traveling wave is incident on the surge absorber, energy contained in the wave is dissipated in the form of a heat generated in the dissipator. Okay, so as and when the surge attacks the traveling wave is incident on the surge absorber, so whatever the energy that is contained in the wave is dissipated in the form of a heat generated in the dissipator itself. Firstly, due to the current set up in it by ordinary transformer action, the secondly by eddy currents. The stiffness of wavefront is also reduced because of the series inductance. The next concept we have is the insulation coordination. It is a correlation of the insulation of electrical equipment and lines with the characteristics of protective devices such that insulation of the whole power system is protected from excessive over voltages. The main aim of insulation coordination is the selection of suitable values for the insulation level of different components in a power system and their arrangement in reasonable manner so that the whole power system is protected from over voltages of excessive magnitude. So this insulation coordination is nothing but the relation between or the correlation between the insulations of the equipment what we want to protect and the insulation of the protective devices. So it is a correlation between the insulation of electrical equipments and the line with the characteristics of a protective devices. The main aim of insulation coordination is a selection of suitable values for the insulation level of different components in any power system and their arrangement in a reasonable manner so that the whole power system is protected from over voltage of excessive magnitude. Thus, the insulation strength of various equipment like transformer, circuit breaker, etc. should be higher than that of a lightning arresters and other surge protective devices. The insulation coordination is thus the matching of a old-time flashover and breakdown characteristic of a equipment and a protective devices in order to obtain the maximum protective margin at a reasonable cost. Here we need to understand the point, the insulation strength of various equipments, that is with respect to the transformer, circuit breaker, whatever we have. So these should have a better insulation strength compared to the protective devices such as a lightning arrestants and other surge protective devices, because as and when there strikes surge strikes, these lightning arrest those surges will pass through these protective devices rather than passing through the equipments like a transformer, generator, circuit breaker, etc. The old time curve of a equipment to be protected and a protective device are shown in figure 10. Curve A is the old time curve of a protective device and curve B is the old time curve of the equipment to be protected. Okay, so from the old time curves A and B, it is clear that any insulation having a voltage withstanding strength in excess of insulation strength of a curve B will be protected by the protective device of a curve A. So this is a curve A. So this is my curve A and this is my curve B. Okay, so curve A is a old time curve of protective device. This is a protective device, whereas this is a curve B is a old time curve of the equipment to be protected. So from these curves A and B, it is clear that any insulation having a voltage withstanding strength in excess of insulation strength of a curve B will be protected by protective devices of a curve A. Then the last concept we have is a basic impulse insulation level. So the insulation strength of equipment like a transformer, circuit, as I have already mentioned, they should be higher than that of a lightning arresters and other surge protective devices. In order to protect the equipment of power system from over voltages of excessive magnitude, it is necessary to fix an insulation level for the system to see that any insulation in the system does not break down or flash over below this level, and to apply protective devices that will give the apparatus effective protection. Several methods of providing coordination between the insulation levels in the station and on the line leading to the station have been offered. The best method is to establish a definite common level for all the insulation in the station and bring all insulation to or above this level. So we need to maintain a certain level, okay, so that all the equipment should be given the same insulation level. This limits the problem to three fundamental requirements, namely the selection of a suitable insulation in the station will equal or exceed the selected level, and application of protective devices that will the apparatus as good protection as can be justified economically. The common insulation level for all the insulation in the station is known as a basic impulse insulation level, known in short BIL, which have been established in terms of withstanding voltages of apparatus and lines. Okay, with respect to the apparatus equipment considered, or with respect to the line, consider what is the level of insulation we need to provide. So there should be a common level of insulation for apparatus as well as the line, that is known as the basic impulse insulation level. So these basic impulse insulation level can be defined as a reference level expressed in impulse crest voltage with standard wave not longer than 1.2 bar 50 microsecond wave. According to IS, 1.5 by 40 microsecond in USA and 1 over 50 microsecond in UK, where that 1.5 is nothing but the surge voltage reaching to the maximum peak value, and 40 microsecond is nothing but discharging to its 50% value in 40 microsecond. That is with respect to USA and UK, different values are there. So apparatus insulation as demonstrated by suitable test should be equal to or greater than the BIL, basic impulse insulation level. So the BIL for a system is selected such that system should be protected with a suitable lightning protective devices, example lightning arresters. The margin between BIL and the lightning arrestor should be fixed such that it is economical and is also ensure protection to the system. The BIL chosen must be higher than the maximum expected surge voltage across the selected arresters. So finally, moving on to the summary of the today's session. So today we discussed the protection against the traveling waves, the 4 different equipments we need to consider: the rod gap, surge arresters or surge diverters, okay, surge impedance, And we also discussed the insulation coordination and the basic impulse insulation level. And in this based on this concept, in the examination you may expect a question: list and explain the equipment used to give protection against a traveling wave. So one thing you need to remember here, while explaining this question, you need to first explain what is the meaning of traveling waves and what are the effects of these traveling wave on the transmission line or equipments, that you need to explain. And then you need to go for explaining the different equipments used for the protection of these traveling waves. And also write a short note on insulation coordination and basic impulse insulation level, BIL. And for this section you can refer the textbooks. And this second book, it is basically used for the explanation of the surge arresters. So for that you can refer the second textbook. Thank you. Have a nice day.